questions about rotational motion, and that might also include about the conservation of energy, conservation of momentum, and all the relevant topics which will be aware with the rotational motion. So the first question is a uniform rod and a uniform rod of length L and mass M is pivoted at one end. Two springs, each having a spring constant K, are attached to the rod, one at the midpoint and other at its free end. The spring pulls in opposite directions, and at equilibrium, their forces act perpendicular to the rod. Determine the frequency of small angular oscillations of the rod about its equilibrium position. So we are going to solve this particular question in two ways, or rather we can say we are going to modify this question into another part also. In this particular question we are only given that there are only two springs. Okay. For that we can just draw an approximate figure. So there is a uniform rod and whose length is given as L, and it is pivoted at one of the end, so it is pivoted somewhere here, and there are two springs that are connected to. One is at the free end, so this is our free end, and here a spring is connected, and there is another spring which is connected to the midpoint, and both the springs are at the opposite. So there is a spring, another spring which is connected to the middle. So suppose this is the other spring which is connected to the midpoint. Okay, so this is the basic figure for the question, and spring constant for both the springs is given as K. Okay, and we have to find out what will be the oscillation when it is from its equilibrium position, it moves away. So we are given that L is the length of the rod. So let me draw only the rod part. So L is the length of the rod, and one spring is connected at the entire length, and the other spring is connected at the midpoint. Okay. So we are going to L, and this length will be L by 2 from the top side L as well as from the bottom side, and the pivot point is just at the end. Okay. And in this case we can assume the axis. So let us suppose the axis is passing through the center of the rod. So on the right side we are going to have our plus x, and on the left side we are going to have our minus x. And therefore the coordinate of the midpoint, let us call this as M, that will be 0 and L by 2. And the spring which is on the left is going to pull towards the left, which is our negative x-axis. Therefore the force we can write, so we can say that we have our springs and springs are connected at two ends. One is at the midpoint So we are going to call this as midpoint spring. And so its coordinate, which we called as our m, will be 0 comma L by 2, and it will be pulling towards leftward. So you can say it is going to pulling toward left. So which is basically our negative x direction. And so it is fixed at some point. So this is the wall to which is fixed, and we can write this as our minus of S1 and L by 2. Okay, because on the x direction we are not given where it is fixed. On the y direction we have the length. Okay. Therefore we can say that, and we are only talking about the midpoint spring. Okay, so it is pulling towards our left side, and we can also say that it's our fixed end is at our minus of S1 and L by 2. Okay. And so we can say the force on the rod will be equal to minus k, and we can call this as E1 and our x unit vector. Okay. And this small E1 is the extension, equilibrium extension. Okay. This E1, we are going to call this as equilibrium extension. Equilibrium extension. Similarly, we have our top spring, and the top spring is having a coordinate of 0 comma L, and it will be connected to the other end, which we can say is our S2 comma L. So we are having our top spring, and this top spring is having a coordinate of, let us call this as T, and top spring is having a coordinate of 0 comma L. Okay. And it will be pulling toward right. Pulling towards right, and whichever positive x direction. And its fixed end is S2 comma L. Okay. And similarly, we can write that force on the rod and that will be equal to over K E2 x unit vector. Now it is said that at equilibrium, so we can say that under equilibrium, And for equilibrium, it is mentioned in the question also that the springs are perpendicular to the rod. So it means they are always about plus x-axis as well as minus x-axis. So we are given that springs are perpendicular to rod. So which basically means they are always about plus and minus x-axis. Okay. And we can also say that, let us call this as point O, which is basically the origin. Therefore we can say their torque about the origin O will be balanced. We can say their torque about point O is balanced. And we already know the forces at the midpoint as well as at the bottom, at the top. So now we are going to find out the respective torque. Okay. So we can say the torque at midpoint let us call this as tau 1, and that will equal to minus L by 2. This comes as our minus K E1, and which gives us K E1 and L by 2. And similarly, we can write for the torque at the top let us call this as tau 2, and our tau 2 will be equal to, this will be minus of L times K E2, and this will be K E2 multiplied by L. Okay. So on the midpoint it is counterclockwise, on the top side it will be clockwise. So obviously one will be positive, other one will be negative. Now for our equilibrium, so we can say our net torque at equilibrium and you can say that our tau 1 plus tau 2 will be equal to 0. So we simply substitute the values, we get this as our Ke1 L by 2, and this comes as minus Ke2L is equal to 0. So obviously length cannot be equal to 0, so we just, and the spring constant is given, so that also we sort it out, and from here we can say that our E1 is equal to twice of E2. Okay. So it means their elongation will be our, on the one side will be twice of the other side. Okay. Now we come to our moment of inertia. So we can say that our moment of inertia, and we know that for uniform rod pivoted at one end, its moment of inertia, let us suppose our I, then this I, because it is at the extreme end, so that will be equal to over 1 by 3, and ml square. So this is a standard formula, and we have to remember that it is for only small oscillations. So which basically means that we can approximate that our sine of theta is equal to theta and cos of theta is equal to 1. That approximation can be made based on our small angle theory. So we can say displacement for small theta, and for small theta we can write that our sine of theta is approximately equal to theta and cos of theta is approximately equal to 1. So therefore let's find out what will be the position of our midpoint from its original position and when it moves toward the left, and the top position that is when it is going to move to the right. And based on this we can say that our midpoint and it moves from 0, L by 2, and the new coordinate will be equal to our L by 2 sine of theta and L by 2 cos of theta. And by small angle approximation we can say that it will be coming as L by 2 times theta and simply L by 2. Now we come to our top point, and top point moves from, and we have our 0, L, and it moves to our L sine of theta and L cos of theta. Once again, with the help of approximation, we can say that we leave over L theta and L. And similarly, we can find out the moment of our center of mass. So you can say our center of mass, initially it will be along y-axis and it is going to move to this will be over L by 2 theta, and we are going to have L by 2. Okay. Initially it will be our 0 L by 2, and it is going to move finally at L by 2 sine of theta, L by 2 cos of theta. Now we come to the torque due to the springs. And we already said that our midpoint spring is pulling towards left, midpoint spring, which is at y is equal to L by 2, and it is pulling left. And for equilibrium, we can say that our spring initial position was 0, L by 2, and it moves towards, suppose through the complete distance, that is our minus S1 and L by 2. And force we also calculated, that force on rod will be equal to minus k E1 x unit vector. Therefore from here we are going to find out the how much it will be displaced. So you can say displaced, and we just found out our displacement, which is our L by 2 times theta, and this comes as L by 2. And therefore we can find out the length. So we can say our length will be equal to, we can simply use the distance formula, that is minus S1 minus L by 2 times theta and whole square, which and next obviously will be our 0, because that will L by 2 minus L by 2, so it's square root, and this will be coming as, we have to take its modulus, so square is going to cancel out here, and this will be coming as minus S1 and minus L by 2 times theta, and this can be, because this negative sign is only the significance is with respect to the direction, so we can say this will be equal to S1 plus L by 2 times theta. Therefore we can approximate that our new extension will be approximately equal to our E1 plus L by 2 times theta. Now we can easily find out the force. So we get our force on rod, which is our F1, suppose, will be equal to minus k E1 plus L by 2 times theta, and this is x unit vector. Now we can find out the change in the force. Change in force, and this change in force is suppose delta F1, and that will be approximately equal to this. We can multiply it, and initially force was our this minus k E1 x unit vector, and therefore this minus k E1 x unit vector is going to cancel out, and we are going to get that the force will be equal to our minus k L by 2 theta, and this is our x unit vector. And the position vector, because we are supposed to find out the torque, so we can say the position vector, which is our R1, and that we can approximate will be equal to our L by 2 theta and comma L by 2. So therefore now we can easily find out the torque. So we can say our torque tau 1 so we have our torque tau 1, and let us suppose with respect to theta will be approximately equal to minus L by 2, and we have this R is our k and x unit vector, so that will be coming as k L by 2 times theta, and we can write this will be equal to minus k L square upon 4 times theta. So this will be our value of torque. Now same analysis we can make for our top spring also. So we can say our top spring and top spring is at the distance of y is equal to L, and it is pulling right. So once again, the equilibrium and that equilibrium is from 0 to L and to the position which is our S2 comma L. And we also know that the force on the rod will be equal to k E2 times x unit vector. So we can find out now our displacement. And for displacement we know that the spring is at the position L theta times L. Therefore we can say that the spring length will be equal to this will be over S2 and minus L theta whole square and square root, and other will be over L minus L, that will this L minus L, that will be equal to 0. So this gives us that it will be equal to S2 minus L theta. So therefore we can say that new extension will be approximately equal to E2 minus L theta, and now we can find out our force. So force on the rod that is suppose our F2 is approximately equal to k E2 minus L theta times x unit vector. Now we find out the change in the force. Change in the force, and that is our delta F2, which will be equal to this F2, and the original force is our k E2 x unit vector. So this k E2 x unit vector is going to cancel out, and that is going to give us minus k L theta and x unit vector. So we whatever this, now we can also, now we need position vector. So we can say the position vector R2 and that will be approximately equal to L theta comma L. Now we are going to find out the torque. So torque, which is our tau 2 with respect to angle theta, and that will be minus L times KL theta. So this gives us minus k L square theta. So we found out the torque, tau 1 as well as our tau 2, and therefore total spring torque spring torque, that is our tau s, will be equal to tau 1 theta plus tau 2 theta, and we get this as our tau of s is equal to minus k L square by 4 times theta, and this gives minus L square theta. So this gives us minus 5 by 4 k L square theta. Now this was only our spring part. Now we come to our, because there will be also mg, and as soon as it moves away from the centralized position, there will be a torque due to the gravity also. Okay, so we come to that part now. So we have our torque due to gravity. And so we know that our gravity suppose the force is given as f of g, and that will be our 0 comma minus mg, and it will be acting at the center of mass. So it will be acting as L by 2 theta and L by 2. And in this case, we assume that this rod is shifted toward the right. Okay, so center of mass shifts toward the right. Okay. Therefore, our gravity produces a counterclockwise torque. Okay. So its torque that is our tau g will be approximately equal to our force, that is our mg, and the distance, which is our L by 2 times theta. Okay. Here I forgot to mention that initially it will be at 0 comma L by 2. Okay. And so we can say this will be equal to our mgl by 2 times theta. Now we find out the total torque due to the gravity and torque due to our spring. So we can say, or we can also write or explain it with respect to our equation of motion. Equation of motion. And for equation of motion, we know that our total torque, if it is represented as tau, then this tau will be equal to our I and double derivative of our theta. So let's find out this tau, that is a total torque. So you can see our total torque, that's our tau, will be equal to spring plus gravity, and this comes as minus 5 by 4 k L square theta plus mgl by 2 times theta. And substituting in the equation, we get moment of inertia, we already know, is our 1 by 3 ml square double derivative of theta, and tau we just found out is minus 5 by 4 k L square theta plus mgl by 2 times theta. So obviously we are interested in this double derivative of theta. Therefore we can write that the double derivative of theta, this will be giving us, or we can just cancel out our length. So this goes square and here the length goes, and rest of things we can keep as it is. So we are going to get this as minus 5 by 4 KL theta plus mg by 2 times theta, and this is 1 by 3 ml. So we are going to just separate the variables with respect to their denominator and take 3 in the numerator. So this will be coming as our minus, and let us take minus as common because we know that there will be a restoring force that is going to generate this or validate our equation, and this will be coming as ml, and this will be 4 ml, and it will be 15 kl. This will be minus, and this will be our 2 ml, and it will be 3 mg times theta. So here length and here mass and mass cancels out. So we get our theta, or double derivative of theta, will be equal to minus, and it will be giving us 15k divided by 4m minus 3g, and this is about 2l times theta. And let me write it moving towards left side. So this will be coming a plus and equal to 0. So this is nothing but equation of our SHM. Equation of SHM. General equation of SHM we can write double derivative of theta plus omega square theta is equal to 0. Therefore, if you make 1:1 comparison, we can write that our angular frequency omega will be equal to over 15k 4m minus 3j 2l and its square root. Now in this case, we are going to slightly modify the question, and let me draw the figure. And for that we are going to add 2 additional springs, and this is a rod. Rest of the parameters are going to remain same. Okay. So this is a rod, and so we have one spring on the top, which is as usual in the first part also, another spring which is at the midpoint. So these are having same spring constant, which is our K. Okay. Now we consider 2 additional springs, and one is at the midpoint, and the midpoint spring is connected toward the right side. Okay. So this is a midpoint spring, and its spring constant is about 2K, and there is our another spring which is connected to the top, and the spring constant is also 2K. rest length as well as mass is same. Okay. Therefore, there will be some change in the equation, but basic concept is going to remain same. So one by one, we are going to consider all the springs. Okay. So the spring constant K, let us call this as spring over S1. Okay. And our of 2K, we call this as our S2. And for this top one, we call this as S3, and on the other side we call this as S4. So these are the 4 springs. So let us consider spring S1. And spring S1 is having a spring constant K. And once again, we consider that it is x-axis and this is y-axis. So obviously this length will be our L by 2 and its coordinate will be 0, L by 2. And it is attached at 0, L by 2. And it is pulling towards the left, and we call this 2 pulling to left and to some fixed point, and that fixed point also we denote by S1 in the first case also, like we did. Okay. So this will be a fixed point, that is minus S1 and our L by 2. Okay. Now we can once again find out the force on the rod and force of the rod at equilibrium. Force of the rod at equilibrium will be equal to minus K E1, and we have this as x unit vector. Okay. And similarly, we are going to write for our spring, which is our S2, and spring constant is our 2K. Okay. And it is also attached at 0, L by 2, and it pulls towards right, pulling right. And it is going to pull right to a fixed point. Let us suppose we denote similarly at S2 and our L by 2. And once again, we can write the equation for the force, that the force at the equilibrium will be equal to spring constant is our 2K. So this comes as 2K E2 x unit vector. And now we come to the top spring. Top spring is our S3. So spring is our S3, constant is our K, and it is attached at 0, L, and it is pulling towards the right. And this is our S3, L. And similarly, we can write its force. Force will be equal to K E3 and x unit vector. Now we come to our final spring, that is our S4. S4 spring constant is about 2K, and it is 0, L, and it will be pulling towards left. and suppose that is our S4 comma L, and sorry, minus S4, second, yeah, minus S1 minus S4. So therefore we can say the force will be equal to, spring constant is minus 2k, and this is E4 and our x unit vector. So once again all the forces are towards our perpendicular, that is plus and minus axis, x axis. So net torque about point 0 about O will be equal to 0. So O point is same, this is our origin. Therefore we can write that our net torque about O will be equal to 0. Or we can say our tau is equal to 0. And so we already know forces, we can simply calculate their torque. So let me, the first case, distance is our L by 2. Okay, let me write it here now. So we have our spring S1, and spring S1 force we already know, and so torque, let us call this our tau 1, will be equal to, distance is our L by 2 and force is our minus k even, and it will be equal to minus k even and L by 2. Now we come to a spring S2. Let us suppose that is about tau 2, and tau 2 is still at the midpoint, so distance is our L by 2, but spring, the force is our 2k E2, and here 2 and 2 cancels out, so this comes as our k E2 times L. And then we have our spring S3. Torque is our tau 3. It's connected at a length L, and our force is our k times E3. So this comes as k E3 times L. And the last one, spring S4. That is our tau 4, and that will be also at the length L. This is minus 2k times E4, giving us minus 2k E4 times L, and net torque is equal to 0. Therefore we can write that our tau is equal to 0, which gives us tau 1 plus tau 2 plus tau 3 plus tau 4 is equal to 0. Now we simply substitute their values. Tau 1 was our minus k E1 L by 2, and this was plus k E2 times L plus k E3 times L minus 2k E4 times L is equal to 0. And this KL we can just move throughout because they cannot be equal to 0, and from here we multiply throughout by 2, So this we get as a minus of E1 plus twice of E2 plus twice of E3 minus 4 times of E4 is equal to 0. And so if we assume that their natural length are 0, or we can say they are equal, okay, so the extension will be directly related to our S of I. I think I forgot to mention this in the first part. Okay, so we can say if the natural length are 0 or they are equal, then we can say that our extension, which we are denoting at E, or suppose E of I, where I is going to vary from 1 to 3 to 4, and this will be giving us S of I. It means E1, we can find out the relationship between our E1 and S1, E2 and S2, E3 and S4, as well as our E4 and S4. So we can make an approximate guess that, because we have to satisfy the equation, so therefore we can just make the approximation that our S1 will be close to twice of S2 and our S3 will be close to twice of S4. So that is our approximate guess, okay, because it is for small angle. And moment of inertia we already know, okay, which we just found out, that moment of inertia is our 1/3 ml square. And now we come to our small angle. Displacement for small theta. So like we said, for small theta, we can write that our sine of theta is approximately equal to theta and our cos of theta is approximately equal to 1. And this, for midpoint, top and center of mass, everything will be same. Okay, the only difference between the two is the springs which are added, additional 2 springs are there. So therefore we can say for midpoint, it is moving from 0 to L/2, and that will be our L/2 sine of theta, which we can write L/2 theta, and that will be a L/2 cos of theta. And then we having top point, and top is from 0 to L, and it goes to our similarly L theta and our L. And finally we have our center of mass. Center of mass is our, it moves to L/2 theta and our L/2. Now let's find out the torque due to springs. Torque to spring, and first is a spring S1, and same process we are going to do. So I can just write, because we know the value of force, we know our length, and we just said that our, okay, let me do it, it will be much more easier. So for our S1, it moves from 0 L by 2 to our minus S1 L by 2, and we know that the force is our minus k E1 x unit vector. So we can find out our displaced. So the displaced length, we get that our length will be approximately equal to same minus of S1 minus, and this will be coming as, one second, I missed, sorry, I missed one point here, yeah. So the the attachment will be with respect to the theta. So this comes as L by 2 theta and L by 2. Now we can easily find out the length. So we can say our length will be approximately equal to, we get this as minus S1 and minus of L by 2 theta, and this is a whole square. Other term will be our L by 2 and our L by 2, that will be 0. So the length will be approximately equal to S1 plus L by 2 theta. Negative is only for the direction. Therefore, we can write that our extension will be equal to E1 plus L by 2 theta, because our S1 is approximately equal to E1. And from here we can say that our force F1 will be equal to minus of K, and we get this as our E1 plus L by 2, and this is our theta. Now we come to the change. Change is our delta of F1, and this is our, this minus this is going to give us minus K E1. One second, I missed something. Yes, I missed it. This is our E1 and this is our theta, and here it will be x unit vector. So we get the force will be equal to, change in force is equal to minus K L by 2 times theta, and we have this as x unit vector. Therefore we can say our torque tau 1 with respect to theta will be equal to minus L by 2, and this comes as our K L by 2 theta, giving us minus K L square by 4 times theta. And now we come to our spring S2. And spring S2 is our 0 L by 2, and it moves to over S2 L by 2, and our force is our 2K E2 x unit vector. And now we can just find out our length. So we can say our displaced length and the displaced length is going to give us S2 minus L2 theta whole square and its square root, which is approximately equal to S2 minus L2 by theta. And therefore we can write our extension is approximately equal to over E2 minus L2 by theta. Therefore our force F2 will be approximately equal to force spring constant over K2, and this comes as E2 minus L2 by theta and this we have our x unit vector. And now we come to the change in force. Change, that is our delta F2, is approximately equal to minus 2k L by 2 times theta, and we have this as x unit vector. And now our torque. Torque will be our tau 2 with respect to theta will be equal to our minus L by 2, and this is our 2k L by 2 theta, and this 2 and 2 cancels out, so we get this is equal to our minus k L square by 2 times theta. Okay. For next two, I'm just going to write the torque directly, and so we have spring S3. Its torque is our tau 3 with respect to theta, which is approximately equal to minus k L square by theta, and we have in spring 4. That is S4. Torque is our tau 4 times theta, and will be approximately equal to minus 2 k L square and theta. So we find out now net total spring torque. Total spring torque, and the total spring torque is, let us suppose our tau s will be equal to tau 1 plus tau 2 plus tau 3 plus tau 4. We substitute the value, we get this as our spring will be equal to minus k L square 4 times theta minus k L square 2 by theta minus k L square theta minus 2k L square theta, and this gives us the tau of spring will be equal to minus 15 k L square 4 times theta. Now we go to the gravity. Gravity will be same because nothing is going to change. So you can say torque due to gravity will be same because the gravity is always going to act at the center of the rod. So this will be mgl by 2 times theta. Now we are going to use equation of the motion. Equation of motion, and which gives us the torque is equal to our moment of inertia times double derivative of theta, and in terms of torque we can write this as torque because of spring plus torque because of the gravity is equal to moment of inertia and double derivative. So moment of inertia we already know is our 1 by 3 ml square, theta double derivative, and this will be our minus 15k L square 4 times theta, and this will be plus mgl 2 times theta, and simply it is, let me put the final equation, that is our double derivative plus 45 times k, and this is our 4m minus 3g 2l theta is equal to 0. So which is also equation for SHM double derivative plus our omega square theta is equal to 0. So So this gives us that our omega is equal to our 45k, and this is 4m minus 3g and 2l and its square root. And okay, from here I forgot to mention that we can also find out the value of the spring constant for stability. First case we can also do same. Okay, so we can say for stability, this term under the square root should be positive. Okay, so we can say for stability we should be above 45 by k upon 4m should be greater than 3g upon 2l. Okay. This can be applied for the first part also, and therefore from here we can say that the spring constant k will be equal to this 2 goes by 4 and this 45 goes by 15. Okay, therefore we get that our k should be greater than, it goes by 2, and the k should be 2g upon 15l. So this is the value of the spring constant that, okay, because other spring constant is our 2k, so we simply multiply it by 2. Come to next question. It states that a physical pendulum is formed by a light rod of mass m and length L with a solid disc of mass m and radius r rigidly attached to its lower end. So we have two parts on it. First, it finds the period of small oscillation about the pivot, and B is how does the period changes if the disc is inserted, a disc is instead mounted on a rod with the frictionless bearing so that it can spin freely about its axis. So for this part B we will come later on. So first of all we are going to concentrate on part A. In part A we are supposed to find out our this oscillation. Okay. So we start with part A. And part A we are given that we are having a, suppose this is our support and it is vertical, and to this we have a light rod, and to this light rod a small disc, solid disc is attached to the this free end. Okay, and it is tight. Okay, it's not free to move. And suppose the small angle is given as theta. Okay, and the rod length is our given as L. So this is length of the rod, and we are given its mass is small m, and the disc is having a mass of capital M, and its radius is given as r. Okay, so we have to remember in this particular case the disc is not free to move, it is rigid. Okay, because in the second part the disc is free to move. So this is the major difference between the two. So we can say disc is fixed, and okay, and for this we already know the standard formula, that is our time period for small oscillation, period for small oscillation, and that is given as t. So the value of t is equal to 2 pi, and this is square root of our I divided by mass, and this mass is total mass of the system, mass total, and G multiplied by D. Okay, and D is the distance of the pivot to the center of mass. Okay. So we have to remember that this distance d is distance from pivot, to center of mass of the system. And in this particular case, the system is of a rod as well as the disc. Okay, so we have to find out its center of mass. So first step is going to that we are going to find out this value of d. So we can say the distance, center of mass distance, whichever d, and for that we need our total mass, or we can just use the formula directly. So we can say that this distance d will be equal to, in the numerator is the total mass, that is m plus capital M, and in the numerator we have our rod whose mass is our m multiplied by that L by 2 plus we have our this disc whose mass is capital M and its distance is from the pivot is given as L. Therefore we get this as our small m plus capital M. L we can take as common, so this will be coming as our m by 2 plus capital M. Now we come to our moment of inertia, and this moment of inertia is the total moment of inertia about the pivot. So first of all we are going to find out the moment of inertia about the rod about the pivot, and the pivot point, let us suppose, is our P. So let's find out the moment of inertia, which is our I, about pivot. Pivot is our point P, and for rod is our straightforward because the pivot point is at the extreme end of the rod, one of the end of the rod. Therefore we can say that our moment of inertia for the rod is equal to 1 by 3 ml square. And in case of disc, first of all we are going to find out the moment of inertia of the disc about its own center, and then we are going to use parallel axis theorem and shift or find out the moment of inertia about the pivot. So we can say moment of inertia, and let us call this as O. Moment of inertia of disc about point O, which we are going to call, because it is center of mass, so this is ICM, will be equal to, whichever standard formula is our 1 by 2 mr square. And for the same disc we are going to find out the moment of inertia of disc about pivot point P. Okay. So we write this as, for our disc about point P, which will be equal to moment of inertia of our center of mass plus mass, and the distance is our L. So this which usually in the formula written as d square, so that will be coming as our L square. Now total moment of inertia, which we are supposed to find out, that is our I. Therefore we can say that our I will be equal to moment of inertia of the rod plus moment of inertia of the disc about point P. So this comes as 1 by 3 ml square plus ICM is our 1 by 2 mr square plus ml square, and L square we can just combine. So we get that our moment of inertia of I, L square we take as common, and this comes as our 1 by 3 small m plus capital M, and this is plus half m r square. So we got our moment of inertia and we already know our mass total. So we simply substitute in the formula, that is our time period is equal to 2 pi square root of moment of inertia I, and this is our mass total G multiplied by D. So mass total is our small m plus capital M, G as it is, D we found out is our, the numerator is, in the denominator is m plus m, and numerator is our L, and we have this as m by 2 plus m, and I we got it as our L square 1 by 3m plus capital M plus 1 by 2 mr square, and this m plus m cancels out, and now it's not much of the problem. If required we can solve it, otherwise that depend upon our what type of solution we are required to find out. So we can say our T is equal to 2 pi, I forgot to put square root, and this comes as our G times L, m by 2 plus m, and here we have our L square m by 3 plus capital M plus 1 by 2 mr square, and its square root. So this was our part A, and now we come to a part B. And in part B, disk is free to rotate. Disk is free to rotate. So it means now we have to here remember that initially in first case we had the disk, and in this case, because the rod and the disk is going to act as a single entity, so as the rod is you can say making to and fro motion, the disk is accordingly moving with it. But in the second case, there is no doubt that the disk is still along with our rod, but this disk is free to rotate. Okay, here disk was fixed, here disk is not fixed, so disk is our free to rotate. So in this case, what is going to happen, that as the rod is going to move make a motion between to its extreme end, this disk is going to rotate about its bearing. Okay, suppose this is the bearing, or we can say that disk does not rotate with the rod. Okay, it only translates with the lower end of the rod. Okay, so the rod, this disk is going to have a translatory motion, okay, and therefore we can assume that this disk is going to behave just like a point object at a distance L from the pivot point. And if it is going to behave like a point object, it is not going to contribute to the you can say moment of inertia. So this is the major difference between the two. So you can say that during oscillations of the pendulum. Oscillations of pendulum, the rod oscillates. But the disc does not rotate with the rod. Rotate with rod. Or from here we can say that it means rod. Rod only translates with the lower end of the rod. With the lower end of the rod. Therefore, we can say that it means rod behaves like a point mass. You can say rod